Hello Chem 242, this is Professor James. I'm just making this video to go over the short answer portion of the exam. If you wanted to see the answers for the multiple choice, you can do so in Canvas. So like I said, we're just going to do the short answers here because we don't have enough time in lecture being in summer semester. So without much further ado, let's get started. Okay, for number one here, it's asking you to predict the major product as well as draw the reaction mechanism. So this is a review problem from last semester. So what I was looking for here is that you showed me the substitution and elimination products here. If you just showed one or the other, I probably won't be marking off here, but this is specifically what I was looking for. I also do want to mention here we have a secondary alkyl halide. So this could be either SN1 or SN2 based off the substrate alone. So the next thing we need to do is take a look at the solvent, nucleophile, all that kind of stuff. So being that we're in a polar protic solvent with a weak nucleophile, this is following the monomolecular route, meaning that it's going to be SN1 or E1. So with that in mind, let's go ahead and proceed. So remember that if you have a good leaving group already, the first step for both the E1 and the SN1 is the leaving group leaving. So let me go ahead and show that, like so. So then we get a carbocation intermediate. We are going to have some rearrangement happening here. So right now it is a secondary, but however you could show a hydride shift with this hydrogen here, and this is going to give us a more stable carbocation. So this jumps over here. And then I like to keep my proper bond angles here. That. So after you have your carbocation, I just want to point out that this one was secondary. This one after the hydride shift is tertiary, and it's also benzylic, meaning that it's resonance stabilized. You could draw the resonance structures for this compound, but I'm not going to worry about it here. Okay, from this point here, you can show two different routes. And I think I'm going to use two different colors here just to show the different possible pathways. So the left one here is going to be the SN1 route. Oops. We're going to show water coming in, not chloride. Almost made a mistake there. So go ahead and have that add on. Nucleophilic attack on the carbocation. This would be racemic. And this is a chiral center. I'm just going to draw it as being flat here. And then I'll just specify at the end racemic. Okay. This step is often forgotten. Students will often just drop off the extra H here, but it is there as part of the water. So then what you can do, let me just go downward here, is you can show a nether mole equivalent of the water. Doing this next step, some people show chloride, but I argue that's a bad choice because chloride is a weak base. So I think water is a better option here. I don't typically mark off if you use the chloride, however. I just want to mention that if it's in water, it's probably going to be water doing this. All right, so this is going to be our SN1 product, and this is racemic because we have a chiral center right there where the carbocation was originally. Okay, and let me go ahead and use red for this next part here. So for the E1 route, what you want to do is show one of the alpha hydrogens. That's going to give you the more substituted alkene. So remember that for the E1 products, you always get the Zastev product because of the carbocation intermediate. So I'm going to selectively choose from here rather than here. If I chose one of these hydrogens up here, it's going to give me a less substituted product. That would be the Hoffman product. Not happening here. So for my base, just like I mentioned here for the deprotonation step with the other route, I'm going to go ahead and use water again as a base. And I'm using red arrows here. So grab the H, form the new double bond, and then we now have the E1 product. And you want to specify specifically the trans product because we do have a carbocation here. You're going to selectively get the trans product here. Remember with the E2, I think I mentioned it in class, with E2, the cis product is possible if the alpha carbon here is a chiral center. But we don't have to worry about that here. Alrighty. Okay, for number 2 here, I gave you guys a, predict the major SN1 product here, but I added the extra complication of the chair conformation. Remember, that's an issue when we're dealing with the cyclohexanes. For this kind of problem, I actually recommend that you redraw it out flat so you're not being confused by what the weirdness of the chair conformation here. And then after you get your product drawn flat, you can then redraw and then predict which chair conformation is the most likely one. It should work out where this large group is axial. So let me go ahead and draw what the 2 products would be. So we do have the possibility of, and I'm going to put IPR, so it's isopropyl that's going to be adding on there. And then we have a methyl. And then we have the 2 methyls over here. It's not a chiral center, but I'm going to draw it that way anyway. That. And then plus an enantiomer. And I just want to be clear here that there's only one chiral center here. It's this one. So we need to consider both possibilities of whether the IPR is up or down. So I'm going to go ahead and draw both versions. So I'm going to go ahead and take this one and just redraw it that way. And then substitute in the IPR for... Actually, it should be OIPR, right? So I'll fix that up here in the drawing. And I also do want to add here, this is probably not the best nucleophile, and this probably would be a minor product here, but this is what I asked for. Okay. Then we could draw the enantiomer. So instead, I'm going to have methyl up and then this one down. Like that. And then this part's the same. Like so. Okay, so recall from last semester that you want the large bulky groups to be in the equatorial position, meaning they're pointing outward. The axial positions are not a good spot due to the 1,3 diaxial interaction. So large groups don't typically go there. So I'd argue that this one probably doesn't even form at all. So what I would do here now is just do a chair flip for this one. And then we'll have the 2 different possible products that would form drawn in their chair conformations. So that one's already okay because the large groups are already equatorial. So I'm only going to chair flip this one. And then that's going to put the OIPR that way, methyl down, and then the methyls over here. I'm going to kind of draw them kind of small because they're not overly important here. I'm mainly worried about what's going on over here. All right, so those are the 2 main products that I'm looking for. Once again, I feel that the trick here is to go ahead and do the problem with it drawn flat. It's probably something you're more familiar with, and then convert to the chair drawings after that. Okay, on number 3 here, what I was asking you for is to show me the major substitution and elimination products. You were supposed to figure out from the conditions here that this is going to be bimolecular, SN2E2. And first things first, we look at the substrate. I'm seeing that it's secondary. That's not really telling me anything. So then I look at the next piece of information, the nucleophile. It's showing here with the full negative. That's a stronger nucleophile. This is going to follow the bimolecular route. So I'm going to go ahead and start off by showing the SN2 product and mechanism. So here, because the way my drawing is, it might be a little bit odd to show the backside attack, but you should get in the habit of showing it coming from the backside of that bond. Kicking this out, and that's basically where we're confirming that we have the inversion of stereochem. I did not specify for chairs in boat drawings this particular problem, so I'm not going to be looking for that if you did it anyway. I do want to mention though that if you were to draw the chair conformation for this, you should be able to get a drawing where both of these are equatorial. So that should be a non-issue. All right, the next thing here is to take a look at the E2 product, and I'm just going to redraw this here because it'll be less confusing, I think. Okay, so for this one here, you need a, I mentioned in a previous problem that there's an issue if your alpha carbon, the one that's getting the H removed. If it's a chiral center, it happens to be here. And remember that the configuration needs to be such that the H and the leaving group are anti-periplanar to each other. Short version is one up, one down if you're dealing with the ring. It's already in that conformation. We're good. So we don't have to worry about getting the Hoffman product unexpectedly. We should still get the Z-step product here because the H and the leaving group are in the correct orientation. So OMe negative. And then let's go ahead and show methoxide here acting as a base. Grabs an H, double bond, kicks out leaving group. And we should have the major alkene product being Zastev, more substituted, like so. And then for these reactions here, if you're worried about mass balance here, we should have chloride as well, right, for both of them. I'm not looking for this, but I'm just including it for the video for mass balance. And it should be overall minus. I did not show a spectator ion with the methoxide. Typically it would be sodium. If you had the sodium spectator here, you would put sodium chloride here instead. For number 4 here, I was asking you guys to rank the following from, I believe it's most to least basic. Let me double check. Yeah, most acidic to least acidic is what I was asking for. So remember we had the acronym ARIO. You should have learned this last semester. This is the order of importance for ranking acidity. It goes atom, resonance, induction, orbital. So seeing here that they're all basically looking at the OH, A is not relevant. We do have R though, resonance structures. So this one has resonance. So I'd argue just from that alone, if we deprotonate this would have numerous resonance structures along this part of the molecule, where neither one of these would. So that automatically makes number 1 the most acidic. The next thing we need to look at is I, the induction effect. So comparing our OHs, the main difference here is the presence of this carbonyl. Remember that's an EWG withdrawing group. And that increases the stability of the anion, which therefore increases the acidity of the OH. So it should be 1, 3, 2 for the order for this one. And I will be looking for a written version of what I just said when I grade this. Okay, for the next one here, I gave you this reaction here and mentioned that the product is actually not produced. And the question is why? And the main reason why has to do with the substitution on the substrate as well as the nucleophile being used here. So we first things first, we have a tertiary substrate which favors the monomolecular conditions, but we're actually being shown what's happening for an SN2. So we're being given the SN2 product for a tertiary substrate that does not work. I also do want to mention that this is a strong base, our hydroxide. So what is more likely to happen here, being that we have a tertiary substrate with a strong base, this is going to follow the E2 route. So we're going to get the E2 product from this as the major product. And there we go. And that's basically what I was looking for on here. So something on those lines about mentioning that we basically have the wrong kind of substrate with the nucleophile. It's going to favor elimination instead. All right, for number 6, I gave you a reaction sequence and asked for all the different pieces in the middle there. So the first thing first, we have bromination. Recall from last semester that you're going to get a bromine substituted in the most stable position. Radicals follow the same stability order that carbocations do. There was an issue with chlorides going seemingly random locations, but bromines follow the rules. They like to follow the rules. All right, so just bromination here, radical mechanism. The second one looks like an E2 elimination, and for the same reason on the last problem, we're not going to get SN2 here because we have a tertiary substrate, but we have a strong base, so elimination is more likely. So we're going to get, for B, the alkene, and you need to make sure you show the Zastev product, so more substituted. because we have a small base. If you had a bulky base there, you would have the double bond going this way, right? Okay, the next one is MCPBA. This is one of our new reagents here. This is going to form an epoxide. This is going to be a syn addition. I'm not going to be picky on the stereochem here on the first part, but something like that is what I'm looking for. The next step here is base catalyzed ring opening. And the main thing I want to see here is that you have your OHs anti to each other, because this is an anti-addition at the end of the day. Because this follows the SN2 pathway. So I'm going to show one OH coming upward, the other one going downward, and then if you want to be thorough, write plus EN or just draw out the enantiomer. That's all there is to that one. For the next one here, number 7, I was asking you to synthesize the following compound here, and I specified that I wanted you to utilize a Grignard reagent and an oxidation, so I was being very specific on what I was looking for here. So the first thing we need to do is functionalize. All we have is an alkane, and the best way to do that is the one we saw in the previous problem, the first step, the bromine reaction. I would also accept NBS here. Typically NBS is used for allylic and benzylic ones, but I've seen it used in this case here too. So I would accept it. So Br. I am then going to do a elimination just like the last problem. So I was kind of trying to help you get started with the last one. I'm hoping you guys recognize that I was trying to help you guys out. So we get elimination here. So, and the reason why I'm doing this is because I need to start working with this part of the molecule now. So there are a couple ways to do this. I'm just showing you what I'm thinking in my brain, but if you came up with something that's, it works and it gives you the same product, and you meet the criteria of Grignard and oxidation, I will get full credit. But we're gonna see all through this semester that there are usually multiple ways to do these. So I'm gonna go ahead and start off by doing an anti-mark addition. And there are a couple different ways to do this. I'm just going to go ahead and use HBr here, and then I'll go into a Grignard reaction. So anti-mark addition with the peroxides, we get that. I'm then going to convert this to the Grignard. Like this. I need one more carbon, and I feel that the best way to probably do this is to go ahead and react it with formaldehyde. So I'm going to go ahead and use that for the next part here. Let me start on the sheet of paper here. So step 1 would be formaldehyde. Step 2 would be a quench with water. And the main reason why I'm doing this is I want to extend that chain by 1 carbon to get that methyl group on there. All right, we're not quite there yet though. We still have an OH we have to get rid of. The 2 ways I'm thinking offhand to get rid of this would be to eliminate with H3O plus and heat and then hydrogenation, or you can convert it to a Grignard and then do a quench. That would also work. So that's what I want to do. I want to go ahead and do it that way because it emphasizes the newer reactions rather than doing old stuff. So, but like I said, you can use some old reactions here to get the same result. So the first thing I'm going to do here is PBr3 to turn that to a bromide. I'm then going to convert it to a Grignard. So we now have MgBr there. I do want to point out you would likely not do this in the lab. This seems rather wasteful to do it this way, but it works on paper. Remember that these are really strong bases. No acidic protons allowed. We basically get the alkane back. So bam, there we go, target. Okay. Okay, number 8 is another one where we have to predict the different intermediates here. I just wanted to mention here that I started off by redrawing this because it's drawn out with the condensed formula showing you all the H's. I like to use the bond line drawing, Cooley structures. Anyway, the first part here converts the OH to a bromine. The second step is the formation of the Grignard. So wherever the bromine is attached, we get MgBr. And then lastly, we have the nucleophilic attack of the Grignard on the carbonyl, followed by a quench. So we should get a secondary alcohol from this, being that we're starting with acid aldehyde and aldehyde. So drawing the product out, so there's our starting compound, new bond, our OH, and then the rest of the aldehyde, which is just one carbon, just like that. And then I would typically redraw it to be, a little bit more appropriate. So we have what? A 1, 2, 3, 4, 5 carbon chain. 1, 2, 3, 4, 5. And then at carbon 2 we have an OH, and then carbon 3 we have methyl. Either drawing is fine, but there you go. Okay, for number 9 here, I was asking for another synthesis question. Show the following transformation. At a glance, I initially thought, this is just hydrogenation with an alcohol, but this is an anti-mark addition, and that reaction does a mark addition, so we can't use that way really. So there's a couple ways to approach this. You could do an epoxide, but that would lead to you having to get rid of the OH on the other carbon. And you could do that with a sequence like I did in the last problem, where I converted it to a Grignard, then got rid of it that way. But that's going to be rather cumbersome. I think a better way to approach this one would be to do the Williamson reaction instead. So what I'm going to go ahead and do here is anti-mark addition of water via the hydroboration oxidation. So BH3, THF, followed by the oxidation step, hydroxides and peroxides. And we're going to get a syn addition. Doesn't really matter. I'm not worried about stereochem here. But we get that. Okay, you then deprotonate. NaNH2. This is a strong base that deprotonates a lot of different things. And then I'm going to go ahead and throw in the corresponding halide, and we now have the target. This last reaction here is the Williamson synthesis reaction. Basically an application of SN2 to make an ether. I did want to point out the trick here in getting these correct is to make sure that whatever side is your electrophile side is less substituted, because this is an SN2. If I were to flip what was what, I would probably get the elimination product as major. So this is better. Alrighty, for number 10, we have another synthesis question. So how do you complete the following transformation? I'm going to start off by mentioning here that I'm recognizing we have a base catalyzed ring opening of an epoxide. So I'm going to keep that in mind as going to be one of the almost endpoints that we're going to go to. So I'm going to start off by kind of working on this piece over here by using a Grignard reagent. So step 1 is the 3-carbon Grignard. Excuse me. So propyl magnesium bromide followed by water for the quench. And I'm not going to worry about stereochem right now for that. But we now have that, and we have to figure out how to get the other piece on there, right? So I'm going to go ahead and do a elimination. I do want to mention that in the real world, you would have possibility of double bond on the ring or on the side chain, because both options would be a tri-substituted alkene. But we're just doing a problem on paper. We're not going to worry about side products there, because I would feel that they're both would be significant. All right, double bond there, conveniently. We now have that. We can then use MCPBA. And then we get the, excuse me, epoxide. And then one more step, base catalyzed ring opening followed by a quench. So we just need to choose the corresponding alkoxide. This is Naomi. No, Naomi is ME, sorry. This is ET. We need 2 carbons there, and then step 2 would be a quench, and then we have the target. Plus EN. You'd have the target and the enantiomer. So there we go for number 10. Oh, and I want to add here again is there are numerous ways to do these. If you guys came in with a 20-step thing, I will be grumpy grading it, but if it's all right, I give credit. I would just be grumpy while grading it if you made one that long. I've seen it before. And finally, at last, we are on the last problem on the exam for the short answers. So this last one here is a spectroscopy question. You have the NMR and both NMRs and some IR information. So first things first, I like to always go to the IR first, as well as do the IHD. So doing an IHD calculation on this, we have 12 H's per 5 carbons. It has an IHD of 0. So no double bonds, no rings. Additionally, the IR data saying there's a peak at 1200. That is a C single bond O. So based off the fact that I have an IHD of 0, and I have, this just a C single bond O bond, that means that my compound is probably an ether. If there were something significant in there, like a carboxylic acid, like an OH peak or a carbonyl stretch or something like that, it would have been mentioned in the IR data. Additionally, if you take a look at the spectra, there's a high degree of symmetry here. We only have 2 hydrogen types and only 3 carbon types. There is only one possible way to put this together. So let me go ahead and draw it out. This is the only possible way that you can put this compound together and have that level of symmetry. There we go. And that is the answer for number 11. So if you guys have any questions about the exam that are not answered in the video, just hit me up on the Discord or ask in class. And I will see you all in class. Have a good one.